So let's talk about finding the domain of functions based on the type of function. Now with a lot of these functions, we're going to get a lot more practice with these in future lessons. We're just going to get a little introduction here. So we've seen it, so that when we go kind of in depth with, say, radical functions, then we already have this foundation for understanding that the domain of that function is limited and how it's limited. So first, let's just talk about linear functions. So a function that graphs a line of some sort. Well, with any linear function, when we're thinking about domain, and really this is true of all of the functions, domain is all about the possible x values. What are we allowed to plug in for x? And when it comes to linear functions, and in fact we can talk about quadratic right now too, because they're going to work in a similar way, so quadratic being a parabola, what we're going to see is we can plug in absolutely anything for x. We can choose any number on the number line and we can plug it in and solve for it. Any real number, it'll work. We can see that with the graphs. We hop over to Desmos real fast. I already plugged in our equations here. So if we look at the line and I think about all of the possible x values, well, no matter how far I scroll away, what we can see is I can plug in absolutely any x value. We're not seeing any holes or gaps or anything like that. So with linear functions, our domain is always going to be all real numbers, as long as it's linear. With quadratic functions, we're going to see a similar thing in that we can plug in absolutely anything. For the domain, we're kind of skipping over range right now. Range is limited for a quadratic, but domain, we can plug in absolutely anything into that function. So, in terms of recognizing these, linear will be your mx plus b. In fact, I'll write that down. Mx plus b. Quadratic is your ax squared plus bx plus c. Which we'll talk a little bit more with that, but having a term that has x squared in there makes it quadratic. So for domain, this is just going to be all real numbers. All real numbers. We can plug in anything. If you want interval notation, we would just go negative infinity to positive infinity for both of those. Where it's going to get interesting are radical and rational functions, and when we start mixing those together. So a radical function typically has a root. We're going to focus on the square root. And what this does, in kind of a general form of what you'll see with the radical, is a shape, it kind of looks like half of a parabola on its side. In fact, it is half of a parabola on its side. We can talk about that more when we get to radical functions. But in terms of a shape, it's like there's a parabola, but we're just looking at half of it. Because if we looked at the whole thing, it would fail the vertical line test and it wouldn't be a function. So, what we need to think about is how we're limited by what we can plug in for x. And what this is going to come from is the fact, and I'll put a little side note here, is that when we have a square root of something, so if I'm taking the square root of some number, I'm going to put in red whatever's underneath there, I'm limited because what's in red there needs to be, or rather let's say it can't be negative. I can't plug in negative numbers underneath the square root. So in terms of setting up domain, something I can do is solve for what I can have for x, or what we can have underneath the square root. And how we're going to do this is we'll take whatever's underneath the square root and say whatever's there has to be more than or equal to 0. It has to be a positive number, or we can take the square root of 0 and that's fine. So let's see how that applies to this example here. What I'm going to do is focus on what's underneath the square root, so that x plus 4 that's in there. In order to find what's okay for x, I need to make sure that it's set up so that x plus 4 is always more than or equal to 0. As a whole, that has to be 0 or higher for that square root to work. And then it's just a matter of solving the inequality. So I would subtract 4 from both sides and have x is more than or equal to 4. And that'll be my domain of the function. So I'll have anything from 4 and including 4 all the way up to positive infinity will work for my function. If you have a radical, this will be the structure that you use. Take what's underneath the radical and set it to more than or equal to 0. Let's look at the graph and see how that works out. So a graph is here, and you can kind of see that half parabola on its side. And what you can see if we zoom in is it's starting at -4 and going off to positive infinity. So that just kind of verifies, and you can use this graphing calculator to verify your answers. To plug in a square root, there's a few ways to do this, but I type in SQRT, and then it turns into the square root symbol, and then you just type in. And then to get out of the square root, you can hit the right arrow, and it will go outside, or you can just click. All right, a rational function. This is where we have a function over a function. So some notation we'll talk about is like p of x over q of x. What basically you'll have a function in the numerator divided by a function in the denominator. And the general shape for rational functions, these can look a lot of different ways, but in general, we might have something kind of like this. This is where we're going to see those asymptotes come up, and with domain, we want to focus on this vertical asymptote. So in terms of having a fraction and thinking about what can't we have happen with x, our limitation is going to be the fact that we have an expression in the denominator, and what we want to be careful of is that that denominator cannot be 0. If that equals 0, then our function is going to be undefined. So in general with these, what we're going to do is if you have a rational function, I'll kind of write that format like I did before. You have something in the numerator, you have something in the denominator. The numerator can be anything. It can be any number, and that'll be fine. Where I'm limited is the denominator, and that denominator is not allowed to equal 0. And that's going to restrict our domain. So, like in the last video where we saw the graph of the rational function, you can see we ended up with just this hole in the domain, is this one spot where our function's not defined, and that's what this is going to solve. So let's see how this works with this example. So what I'm going to do is take the denominator, and you can just ignore the numerator. So take the denominator, 3x plus 4, I'm going to say that is not allowed to equal 0. Then I'm going to solve for x just like I would in an equation. It's just our symbol is does not equal instead of equal, but it works just the same. So subtract 4 from both sides. So 3x cannot be -4. Divide by 3, and I'm seeing x is not allowed to be -4/3. So from a domain, if I put an interval notation, I would say we can have anything from -infinity up to -4/3, but not including -4/3. And then starting at -4/3 but not including it, and going off to positive infinity. So if we take a look at the graph for that, we can see my function is defined everywhere except, it's kind of hard to see here. In fact, I could create the line x equals -4/3. There we go. There's a nice visual for our vertical asymptote that our graph will get so close to, but not equal. So with that, we can see where our function's defined absolutely everywhere except for that one spot. Now our last piece here, and this is one we'll practice so much more, but what if we mix some pieces? And with that, you just want to mix the restrictions that we talked about up above there. So I have two pieces. The denominator is not allowed to equal 0 because this is a rational function. What I also have is 3x plus 4 has to be more than or equal to 0. Coming from the radical symbol and what's underneath there. So what you could do is separate these up and solve. You could even combine them, because if what's underneath there, that 3x plus 4 has to be more than or equal to 0, but at the same time we're saying it can't equal 0. So if we just combine those two, we could solve it in one piece by taking that 3x plus 4 and saying it has to be strictly more than 0. We lose the more than or equal to because it's not allowed to equal 0. So you can either solve separately, or this would combine it into one big calculation. So I'd subtract 4 from both sides, divide by 3. So I'm seeing x has to be more than negative 4/3. It also can't equal negative 4/3. So I'm going to start at negative 4/3 and go off to positive infinity. And let's look at the graph of this. So get rid of that, and I'm just going to make a square root 3x plus 4, and then delete that piece there. And actually I'm going to bring back that x equals negative 4/3, because what I'm getting here is a vertical asymptote. It's getting super close, but as soon as we zoom in, there's going to be space between them. So it's getting super close to negative 4/3, but does not equal negative 4/3. But then we're defined all above there. So we can see our domain goes off to positive infinity. Okay, so that's how we can find those algebraically. Again, we're going to have a week with quadratic functions, a week with radicals, a week with rationals. So we'll revisit those ideas then, but just a little glimpse at what's coming up.